Star Trek critters, and they're like roughly spherical shaped, and they're completely fuzzy. They're covered in fur. Show it to you because it actually helps understand some of this is what they look like. Picture of them, they're just these. You can actually buy stuffed animal versions of these. They're just these fuzzy things. So it's like a sphere with a bunch of fuzz on it. Now let's imagine this tribble. You're tired of all this fuzz. It's going in all these different directions, right? And it's just too much. So you want to comb that fur. Put the mouse over here. You want to comb all the fur flat. So you imagine you don't have a regular tribble, but you have one with infinitely thin fuzz and perfect fuzz. So it's like mathematical fuzz that is perfect. In that it's in mathematics we often have these perfect versions of everyday objects. For example, sometimes we would you imagine there isn't length. Actually, when we calculate anything, like when we imagine how long it takes to get to a destination, we actually neglect general relativity. So actually all of Newtonian science and Newtonian math is actually a mathematically simpler version of our universe that we use for convenience sake when thinking about stuff. And similarly, you could imagine, well, it wouldn't really be simpler, but a tribble or sphere which would have all this fuzz, and we want to comb it all flat. So we could try combing it around. No matter how you comb it, you cannot comb it all flat. If you want to comb it continuously, you can't comb it all flat. And that doesn't really make sense, but if you try imagining it, try to comb it completely flat, you can't do it. If you have a one-dimensional sphere, let's look at the different dimensions and see which ones it's possible to comb these things flat for, and we'll see if we can find a pattern. So in 0 dimensions, you can't really have anything. One-dimensional sphere, it's a line. You'll have one fur here, one fur here, and you can't compress them. You have to comb them, so it doesn't work. So one-dimensional, you can't comb that flat. Two-dimensional, you'll have a circle. You'll have hair going out like this. You can comb it completely flat. Just comb it all around. Two-dimensional, it works. Three-dimensional, no matter how you try to comb it, you cannot continuously comb it completely flat. There will always be like one hair sticking up here, or the other pole. It won't work. So three-dimensional, it doesn't work. Four-dimensional, you have a four-dimensional hypersphere with all those hairs on it. You can comb it flat. I've tried imagining how to do it. I might have got close, but I didn't give much time to it. But it's been mathematically proven that it works for a four-dimensional hypersphere. It works for 4D. 5D, it's been proven it doesn't work. And in fact, every even dimension, it works, and every odd dimension, it doesn't work. So if this fuzzy ball is an even amount of dimensions, then that means that you can comb the hair entirely flat, but if it is odd dimensional, like 3D, you can't. And you might wonder, how do you comb your hair completely flat? Well, it's because, you don't have to, that's not a complete sphere, that's only, part of a rough sphere. So that's just a part of it. So that's different than combing a whole sphere, like a tribble, like I showed you. Alright, and n-dimensional platonic solids. Platonic solids. So I told you there's 6 four-dimensional platonic solids. In one-dimensional, we have one platonic solid, the line. In two-dimensional, we have an infinite amount of them, the regular polygons. Three-dimensional, we have those 5 polyhedra. In four-dimensional, we have 6 of these 120 cell, there's a 600 cell. We have the tesseract. In 6 dimensions, we have 3. In 7, you've got 3, and 8, you've got 3. They're all analogs of the ones before. And basically, from 6 dimensions onward, there's only 3 platonic solids. There's not much to talk about with that. And now I'll talk about E8. So imagine you have oranges in a cart. These aren't regular oranges. These are mathematically perfect oranges. So they are perfectly spherical. And you want to put them in this cart the way that they'll fit the best and will have the least amount of gaps per orange. So why don't we think of a simpler problem first. Imagine you have one-dimensional spheres, just lines, and you want to arrange them so that they have the most efficient space, packing space. You can put them next to each other, and you can have 100% of the space used up by just the lines. In 2 dimensions, it's not as easy because you're going to have some space. You can't fit circles perfectly well together without any gaps. You can do this pennies on a table. What you'll find is that the best way to have them is in this hexagonal formation. Again, I'll use this screen share here. you what that looks like. I'm sure you all know what it looks like. 2D circle lattice. Right, so like here, this one right here. Oh, I don't have screen share on. Screen share with. Oh darn! I have to do this thing all over again for it. Alright, so this one over here. Hexagonal packing is the most efficient way to pack 2D spheres. So you'll notice that there are gaps, but they're really small gaps. Not this one, ignore this one. This is inefficient, but this one there is more efficient. Oh yeah. In 3 dimensions, if you want to pack 3D spheres, you simply you kind of have hexagonal lattices, and then you kind of stack them in such a way. And when you do that, you have an efficient packing of 3D spheres. But you'll notice that there are a lot more gaps than the 2D packing. They're bigger gaps, and it's a little bit harder every step up dimensions to figure out the best way to pack them. And the gaps will always grow bigger. In 4 dimensions, there will be bigger gaps between the spheres. The gaps will be more numerous. In 5 dimensions, there'll be even more. In 6 dimensions, will be more. 7 dimensions, we don't even know what the optimal way of packing them is. In 8 dimensions, 8-dimensional spheres, the gaps are so big that you can just fit whole new hyperspheres in them, and you can actually have this more efficient lattice, 8-dimensional spheres. And that's called E8. The E8 lattice is this lattice of 8-dimensional spheres. And they do have fairly big gaps, but not that much actually, because a lot of those gaps are actually filled in with other hyperspheres. And then it kind of continues to happen on. The gaps get bigger and bigger again until at dimension 243 or something, there again is space for more hyperspheres in those gaps. Alright, so we're